All right, so today we're going to be talking about exponents. This will be a little bit of a review, at least at the beginning, as we move forward. And so first off, we got to think, what does it mean when there's an exponent here? So a is just a number. Here we've got a cubed. What does that mean? That means we're multiplying a by itself 3 times. A times a times a. And if we have, a to the n, well, then that's just a multiplied by itself a total of n times. So what happens when we have a cubed times a squared? Well, we've got 3 a's and then 2 a's here. How many a's do we have? Well, we got 3 plus 2 of them. Or simply a to the 5th. So if you've always wondered why do we add exponents when it's like this, this is the reason. And so more generally, when we have a to the m times a to the n, it turns into am times an. All right, so moving forward. What happens when I got a cubed and then I'm squaring the whole thing? Well, that means I got 2 a cubes, like so. And so we got 3 2 times. So this is simply a to the 3rd times 2, or simply a to the 6th, 3 times 2. And so in general, when you've got one on the inside, one on the outside, you just multiply the two together, and that's your exponent right there. Anytime you see a -1 on the number, that just means that it's going down to there. And if it's a number other than 1, you just put it downstairs with that number in, whatever it happens to be, like so. Next exponent, when we've got a cubed divided by a squared. So note we got 3 a's in the top, 2 a's in the bottom. Right? Each a cancels out, leaving 1 left. So it's simply the amount of a's that were on the top minus the number of a's that were on the bottom, which simply gives us a to the 1st. And of course, if I just write a, the 1 is implied. So anytime I've got a to the n divided by a to the m, it's just a to the n minus m. Now the rational exponential form of a square root here would just be a to the 1/2 exponent. And if it's, and note the 2 right here is implied, or it could be like a cube root, a 4th root. If it was a cube root, I'd put a 3 here. If it was a 4th root, I'd put a 4 right there. And so in general, whatever root you have there goes in the bottom of the fraction and the exponent. Now, what happens when I've got a to the nth root of a to the m? Well, note that this is the same thing as a to the m raised to the 1 over n. Using one of our previous rules, we just multiply m times 1 over n, giving us a raised to the m divided by n. And note, I can rewrite this as a to the 1 over n, and the whole thing is raised to m, and that's the same thing as the nth root of a raised to the m, or simply dropping the parentheses. Actually, let's keep the parentheses. It looks funny without it. So you can rewrite it like that. So let's just do a quick example. Let's say I've got 2 raised to the fourth, square root it. There's more than one way to solve it. I could just take the exponent first. Right? 2 squared is 4. Double it again to get 8. Double it again to get 16. And so we do the square root of 16, which of course is just 4. Or we could say the square root of 2 to the fourth. Well, that's the same thing as 2 to the fourth times 1/2, which is 2 squared, and we get 4 again. All right, so make sure you're familiar with all these exponential rules. They are very important to understanding the material. All right, so now we're going to talk about a linear model versus an exponential model. So for a linear model just means that every time you progress 1 unit, you increase what you're doing by 2. Very predictable. So at -2, when x is -2, we're at, of course, -4, and then -2, and then 0, 2, 4, 6, 8, 10. Right? And each of these, we just increase by 2. Now, 2 raised to the x, by contrast, you double every time you go up a unit. And so here we got 2 to the 0. And just as a reminder, anything to the 0th power other than 0 itself is 1. And so, you know what? Why don't we go back and let's add that to our rules. I'll put that up here. A to the 0th power is 1, provided, of course, that a does not equal 0. All right, so 2 squared, 2 to the first is 2. Note that, just double that. All right, and then 2 squared is 4, double. 2 to the third is 8, right? Double 4. 2 to the fourth power is 16, and 2 to the fifth power is 32. Going the other way, 2 to the negative first is a half. Note that 1 is twice of a half. And 2 to the negative 2 is a fourth. And again, note that a half is double of a fourth. And so you can see how the exponential model grows a lot faster than the linear model. So let's look at this visually. So we're going to go ahead and plot these. First, we plot 2x. And so for 2x, right, goes through the origin and then just goes up by 2 units every time I go to the right one in this nice, predictable fashion. Ignore that point. Just like so. And again, that is y equals 2 times x. Now, 2 raised to the x, right, when x is 0, we're at 1. And then we go 1 to the right, and we intersect. And then we go to 2, and now we're above. I'm sorry, we still intersect, right? It goes, but we go above after that. So when we get to the third, we're up at 8. And then we're off the page. Going here, a half, a fourth, and then this would be at an eighth. And so you can see from the graph, as we move to the right, y equals 2 raised to the x is shooting off the page much sooner than 2 times x. So here at the bottom, note that the exponential function grows exponentially faster than the linear function. So note that in English, when we use the word exponentially faster, we just mean something is moving just so much faster than something else, the human mind can't even comprehend it. All right, and so what is the exponential function? The exponential function is 1, 2, 1, right? It passes the horizontal line test. They both do, the linear model and the exponential model. So we're going to now take advantage of the fact that the exponential function is 1 to 1. And so when we're looking at two sides of an equation where we have exponent on both sides, if the bases are the same on both sides of the equation, you can set the exponents equal to each other. All right, and that's exactly what we're going to do in these examples. We got 10x equals 100. Well, note that 100 is the same as 10 squared. The bases are the same, 10 and 10. So we set the exponents equal to each other so that x equals 2. And that's the value of x that makes this statement true, because 10 squared is 100, of course. All right, next we've got e, the natural number e, also known as Euler's number, 2.7 and some change. And so we've got e to the first power minus 5, which is e to the negative fourth. Exponents are now the same. X equals negative 4. That is our answer there. All right. Now there's a couple of different ways to solve this one. We're just going to, we'll do the most straightforward way first. Divide both sides by 5 to get 1/5 raised to the 2x equals 1/5. And note that'll just be to the first power. Bases are the same, 1/5 and 1/5. And so we set the exponents equal to each other and find that x must equal 1/2. Now, another way we can do this, not quite as straightforward, we'll call it method 2. We could say 1/5 raised to the 2x times 1/5 to the negative first exponent equals 1/5 to the 0th exponent. So 1/5 raised to the negative 1 power is simply 5. To get back to here, any number raised to the 0th power is 1, which gets us back to there. And so now we combine these two to get the exponents to be the same. And so we have on the left-hand side 1/5 raised to the 2x minus 1 equals 1/5 raised to the 0 exponent. Bases are the same. And so we set the exponents equal to each other. Solve this guy for x. Add 1, divide it by 2 to both sides. And x equals 1/2, which is the same as what we got before. Okay. This one's more straightforward. This one allowed us to explore the different exponential rules that we went over on the first page of this handout. All right, so right here. Note we can divide both sides by 4. And this gets us 8 divided by 4, which of course is 2. And right here, I can distribute this 2 so that I've got 1 squared divided by the square root of 2 squared. Of course, the x is still hanging out here. And that gets us 1/2 raised to the x equals 2. And 2 is the same thing as 1/2 raised to the negative first. 1/2, 1/2, the bases are the same. So I can set the exponents equal to each other and find that x must be -1. -1 is what makes this whole thing work. Okay. Next page. All right, so here we've got some models, mathematical models that we're going to take advantage of. Here we've got a nuclear reactor that initially produces 200 kilograms of cesium-137. How much cesium-137 remains after 100 years? And here is our mathematical model right here. And the constant, the exponential decay constant for cesium-137 is -0.0231. And this constant is experimentally determined. All right, so we've got a time frame of 100 years. And our initial amount of cesium was 200 kilograms. Okay, we want to know how much at time t. So AT is 200 times e raised to the negative 0.0231, negative. And that's being multiplied by 100 years. Or more simply, 200 divided by e to the 2.31. And after that point, you just plug it in your calculator to get the right number of years. I'm sorry, I said number of years, number of kilograms after 100 years. So when you plug that into your calculator, you'll find that there are 19.8 kilograms. And we'll say 200 point for significant digit purposes. So you started off with 200 kilograms, and after 100 years, you still had about 20 kilograms. All right. Now we're going to do a different model, but I want us to note that there are definite similarities in these two models. One was a physics, and the other one is banking. Here we've got compound interest. You put $10,000 in a bank account with an interest rate of 8% per year, compounded monthly. If you do not make any withdrawals, find the value of the account after 3 years. All right, so N in this case is the number of compounds per year. And if it's compounded monthly, well, that's 12 compounds in a year. Now the rate, or the R is the rate, and that will be the annual rate. Which we have at 0.08 to correspond with the 8%. Note, I don't write 8%, I write 0.08. And this, again, will be compounds per year, and this would just be per year. Now, there's two different types of rates. You got the annual rate that we talked about. There's also the effective rate. And the effective rate, RE, the effective rate, and that's just the rate per compound period. And that's found by simply taking the annual rate and dividing by the number of compounds. Note that the effective rate is built into the equation, R divided by N. So a lot of the times I'll calculate the effective rate beforehand, so that way I don't have to do so many inline calculations. All right, and it's worth noting that T stands for the term, and that is the time in years of the loan, right? Term is basically the life of the loan. And in our case, that would be 3 years. And our effective rate, let's go ahead and calculate that, 0.08 divided by 12, which is the same as 8 over 12 divided by 100. And 8/12, 8 and 12 are both divisible by 4. So 2/3 divided by 100. Now, 2/3, that's 0.6 repeated. Still divided by 100, or simply 0.006 repeated. That's how you could figure that out without a calculator. All right, so we have all this preliminary work done. Let's go ahead and solve the problem. We want to know how much money we're going to have in our account after 3 years. P. P is the principal. Principal is just how much money the account starts off with. Okay. Note that the principal is analogous to our starting amount of cesium 137 from the previous problem. And our principal was $10,000. All right, so putting all this together, we got 10,000 times 1 plus 0.006 repeated, raised to the nt. Nt is the total number of compounds, right? Compounds per year times the total number of years. And so we got 12 compounds per year multiplied by 3 years. Simplifying this to like that, and then 12 times 3, that is 36. Now, unfortunately, that's about as far as you can go without a calculator or a slide rule if you're old-fashioned like that. Otherwise, we break out the trusty calculator. And so we have 10,000 times 1.0. We'll just put a bunch of sixes on there for repeated. And then raised to the 36th power. And according to this, hold on, I left off a 0 right there. So second insert 0. There we go. 1.006 repeated, not 10. We'll have $12,702 and 37 cents. So that means that the total amount of interest that we earned on our $10,000 was $2,000 or $2,702.37. And all we had to do was to go without our $10,000 for 3 years.